his PhD in deep water sedimentology from University College Dublin, Ireland. His research interests include source-to-sink sedimentology, deep sea carbon cycle, and silicate diagenesis. He has published in leading journals such as Sedimentology, Marine and Petroleum Geology, and Journal of Greenhouse Gas Control. Arif is recipient of several international awards from reputable research organizations such as SciNTIF, AAPG, IAS, SEPM, and Marine Institute Ireland. I would like to ask Dr. Arif Hussain, please come to stage and give your talk.
Thank you very much. It's glad to be back to Institute of Geology after so long, and thanks to the organizing committee for inviting me for this talk. So much of the morning, like the previous presenters, they have really neatly sort of documented the large-scale processes and sort of controls on sediment supply and then their transport to the deltaic sort of settings or shelf sort of setting. Well, my talk will focus a bit on the smaller scale that we call depositional event scale or event bed scale, which is kind of the fundamental building block of the deep water stratigraphy. So whatever any event records is kind of, it records all the details of the processes and related fractionation of its particulate load. Before starting, I would really like to acknowledge these organizations and particularly these people, Peter Horton and Pat Shannon, who are my PhD supervisor at UCD. Emma Morris, a very good friend of mine from Utah, Colin Pierce from Cambridge, and Jenny Omar from Rocktype Limited. So thanks to them. So this is a brief outline. Like in the first part, I will try to build a case for sediment gravity flows is a vector of carbon mass transfer to the deep sea. Then definitely we will talk about existing models for carbon burial in the deep sea. Then I will go and discuss from the very sort of introductory sort of idea about hybrid sediment gravity flow deposits and the processes related to them, definitely because most of you are undergrads, so perhaps it would be really interesting for you to understand where we are in terms of deep water sedimentology. Then I will show rather cool flume sort of experiments, really simple sort of experiments, experimental sedimentology in the lab, and then the understanding that we have from the experimental sedimentology, then we will build on that and then try to cover the similar sort of aspect in the deep time carbonaceous outcrops on west of Ireland. Although they are really deep time deposits, perhaps they are not very much related to Pakistan in terms of location, but their implications are equally important for the fans that are lying at our doorstep or deep water sea systems. And then conclusion. So what are submarine or deep sea fans? They are the net accumulations of terrestrial sediments, organic matter, and most recently anthropogenic pollutants that we call microplastics, since we are living in Anthropocene. So there is a new sediment in the market or in the academic circle that we call microplastic. So it's a new type of sedimentary particle. So deep sea fans are sort of accumulations, net depositional accumulations of those sort of particles at the terminal end of this rather long land to deep sea sediment transit. So basically what happens is that sediments are generated at the source, like at mountainous regions and from under the influence of precipitation and climate and all that, all those factors, and then it's being carried by those sort of slow processes to these lowland areas, such as valleys and wadis, and from where they are picked up by those river systems and brought to delta. And from deltas, they continue their offshore journey or deep, where with the help of sediment gravity flows. Why deep sea fans are really important? They are important because they are the largest sediment transport agents on Earth. You know, a single sediment gravity flow event can transport the amount of sediment that is transported cumulatively by all the major rivers per year. So this is the level of those flows. And the amount of organic carbon within these flows is very high, so much so that it can really impact the long-term carbon cycle and climate and the deep sea sort of ecosystem. So very important. This is a really nice diagram from Bob Helton and Joshua West, where they sort of showed the different source and sinks, quantified view of those different source of sinks of atmospheric carbon. An interesting part is that the deep sea or the organic carbon burial in those sort of deep sea environment is kind of the second largest carbon sink. So they represent the second largest global CO2 sink. So really important. Deep sea fans are also very important because they are lying at our doorstep. At the eastern side of Himalayas, you can see the biggest sedimentary deposit on this planet. We call it Bengal fan. And on the most southwestern part, we got our Indus fan. And speakers before me, they really worked really well, and they showed really well sort of how sediments are sort of brought in and deposited in the Indus Delta plain. But just to give you an estimate, that the Bengal fan just transport over 1 billion tons of sediment per year to the Bengal fan. So really high amount of sediments. And it's very well established now in the literature that it has contributed to the Cenozoic cooling trend. So if you Google, you can find that Cenozoic cooling trend, what it was. There is a really nice paper from Walir Ghali and his team on this efficient organic carbon burial in Bengal fan. So if anyone is interested, they can refer to that. Okay, as I mentioned that sediments from the shelf are carried by those sediment gravity flows. So there are two main sediment gravity flow end members. One is called turbidity currents, where the turbulence and grain-to-grain interaction is kind of the main depositional mechanism, whereas the other end member is this debris flows, where metric strength is kind of the main grain particles or sediment depositional mechanism. So turbidity currents and debris flow, just keep it in mind. Okay, so this cartoon sort of show how then from the shelf, this organic carbon is being taken by the sediment gravity flow. So it's taken from the delta. The mixture of sediment is sort of cascade down those sort of submarine canyons, and then they are picked by those channels and brought to the distal ends of the fan. So you can see this finger-shaped or other radial-shaped bodies that we call lobes. So these are the net sort of depositional accumulations of the sediment. Definitely sedimentation also takes place in channels, but in case of confined sort of channels, it's more it happens more in the lobe settings. And recently lobes have been established as a mega sinks for carbon. So there are some really nice and interesting papers there. So if anyone wants to read about them, they are there. Okay, so now what are the existing models? What are the existing models for carbon burial in the deep sea? Traditionally, we have been thinking that these deep marine mudstones are kind of the sink for carbon burial in the deep sea, where sediments are kind of settling from these slowly settling suspensions, and they are accumulating there. But the problem with this sort of model is that when sediment is slowly settling, it can be exposed to oxidation and also to marine microorganisms, which can really degrade or oxidize it. So essentially, organic carbon burial is perhaps is not that efficient with this, and there is a bigger conundrum in the deep water sedimentology, which is that there is a missing carbon. The amount of carbon in the shelf sediment and the amount of carbon buried in the deep sea so in the deep sea the amount of carbon buried is 50% only compared to the shelf sediment. So it's half of the shelf sediment. Where is this all missing carbon going? Like first model was this really deep sea mudstones, but the depositional process is kind of favoring its degradation. More recently, there is another concept, carbon burial by turbidity currents. Really, so more coarser grained sort of facies in the submarine system can also bury organic carbon, mainly in the BOMA TB or TD or TE sort of divisions. But the problem is that these fine-grained sort of divisions of these fine-grained facies represent a small part of the turbidity currents. And still there are there is still some ongoing debate about the origin of these beds, whether these are really turbidity currents or they are some sort of matrix-rich or hybrid sort of beds. So now my favorite, hybrid sediment gravity flows. So a turbidity current that is going downslope, what it does is it erodes a lot of muddy substrate from below, and then what it does is it segregates that or fractionate that mud load into the tail regions of the flow. So erosion takes place on the frontal part, and then this sort of sediment is being sort of transported or segregated towards rear of the flow. And mud is by nature cohesive, yeah. So when it crosses a certain threshold, it will begin to form the sort of a gelling sort of structure, and the deposition is suddenly changed from really incremental sort of deposition to en masse or rapid freezing. So when mud crosses a certain threshold, everything which is there is suddenly captured and load is deposited. And so consequently, the deposits then we have are kind of part turbidite and part sort of debride. So in a single sort of event, you can have a turbidite part and debride muddy rich part. So this phenomena has been explained by Peter Horton in his seminal paper in 2009, and the deposits are called hybrid event beds. So hybrid means that a turbidity current is showing more than one process of deposition. So hybrid event bed has 5 parts, the lower sandier part, which is deposited by a turbidity current from the front region. Then we have this H2 division, which is a sort of cyclic alternation of sand and mud. This is sort of indication that flow is beginning to change its character. It's commonly not expressed in the natural deposits. And then this most important H3 part, or perhaps my favorite part, which is where sand and mud and organic carbon and everything is sort of mixed up just because we have rapid deposition because of clay. And then they are capped by those 2 divisions, H4 and H5, which are kind of more related to the BOMA mudstone cap sort of terminology. Hybrid event beds really dominate the lobe stratigraphy. So they are frequently occur in these sort of lobe settings in many configurations. They can be throughout the lobes stratigraphy. They can be at the bottom, at the center, or at the top. It doesn't matter. What's important point is this: they dominate lobe stratigraphy. If we see what are the applications of hybrid beds, like they are barriers to the fluid flow in subsurface. So this is a hybrid bed from the Cretaceous Lysing Formation offshore Norway. And what you can see that this is permeability. So permeability is varying by several orders of magnitude. You have 1,000 to 10,000 millidarcies, and then you have 10 to 100,000 millidarcies, and then you have some zones where you have sort of really low permeability. Interesting part is this bed where permeability is sort of practically zero. And then there is another bed, which is again permeability begin to increase. So if you imagine those sort of beds in sort of 3 dimensions, and their aerial extent, you can realize that they are barriers to the vertical and lateral sort of fluid flow. So this was sort of conventional applications of those hybrid beds. The idea was well received by oil industry, and it's continually used by this. Anyhow, this is not topic for today. So hybrid beds are widespread. They are occurring in all sort of deep water systems. At least I know more than 2 dozen of deep marine systems, both modern and ancient, where these type of deposits occur. Like I have shown you some really famous examples from Gulf of Mexico, from Permian Basin, from North Sea, South Atlantic, and Taiwan Strait. I mean, like the phenomena is really widespread. A common factor between all these sort of hybrid event beds is the clay. So clay is sort of culprit, because when it's entrained, it crosses a certain threshold, it forces the flow transformation and deposit all sand and mud together, which is kind of really bad for reservoir quality perspective. But it's also sort of blessing in disguise for carbon work. Now, how clay can really impact the depositional processes? I think so. I will try to show now a few flume videos that we have simulated back in 2018 at University of Bangor with Jakobas and his team, and those sort of flume studies will clearly demonstrate how clay can impact depositional processes. So, sorry for a bit of break. So we just took simple clay, it's bentonite, very cohesive clay, and we put it in the water and run it over this flume, rectangular sort of flume tank. So this is the first flow, which is kind of with 13% of bentonite. And what you can see with 13% of bentonite is flow is behaving like a turbidity current with, sorry. So back to the business, 13% of bentonites, fairly like flow is behaving like a high density turbidity current with quite a lot of turbulence on the top region of the flow, fairly mobile, and flow is almost travel like 14 feet on the flume tank. So if I play it again, you can see it. 13% bentonite, fully turbulent flow, moving fast, quite mobile. So deposition from such sort of flow will be incremental, sort of incremental sort of deposition. First en masse and then incremental. So it's fairly mobile as well. It covered considerable distance before it was frozen. Sorry. Sorry, these videos are a bit heavy, so they might take some time to load, but anyhow. So now what we did with the flows is just we increased 2% of bentonite. So now our flow is 15% of bentonite. And you can see how it's behaving dramatically different. Not quite a lot of turbulence. I'll play it again. So 15% bentonite, fairly less mobile. There is a little bit of turbulence towards the top, and it's less mobile, so it covers almost half of the distance. So first was up to 14 sort of feet, and now with the 2% increase of clay, there is no turbulence, and flow is much less sort of mobile. Now I'll show a third experiments with 17% of bentonite. So this is a flow with 17% of bentonite. Virtually, there is apparently no turbulence. Flow is frozen and it's rapidly arrested. 17% of bentonite. Flow is practically immobile and it's just suddenly frozen. So now imagine that you have those sort of natural sort of sediment gravity flow, which is a mix of sand, organic matter, mud, microplastics, and all that sort of fragments. And what they do is, so when mud crosses a certain threshold, these sort of flows can rapidly dump its load. So organic carbon is there, which is also rapidly deposited. Yeah, so it's not exposed to that sort of suspension processes that you will normally see in the mudstones or the mud caps of turbidity currents. Back to the slide. Sorry for this quite discontinuous sort of journey. The files are very heavy, and I just really wanted to show you about this fascinating experimental sedimentology field, which could be a future field for many of you. So just wanted to show you this. Yeah. शेयर हो गया, हाँ बस हो गया, मिलिएगा। हाँ ये so sorry for discontinuity. So clay is sort of the main mechanism that really controls the deposition within deep marine settings. So flow tanks are gone. Now I'll take you to the west of Ireland in a deep time. So we have there is a sediment. This was a part of my PhD. We have a sedimentary basin that we call Clair Basin. It's on the western flank of Ireland. And the basin has about more than 2 kilometer thick strata. At the basal part, it has this deep water mudstones, and then it's on top of that we have these deep water turbidite deposits. On top of that, we have those coeval slope systems that pervaded into the basins, and on top of the slope system, we have sort of this fluvial sort of system. So the basin is really nice from source to sink sort of sedimentology, and it lends itself to the source to sink sedimentology approaches. That basin has been sort of studied extensively for over 100 years for oil exploration. So our focus was Ross sandstone formation, which is a deep turbidite system, really sand-rich, up to 70% of quartz, sand, and 30% of mud sand-rich turbidity system. And these deposits are also kind of really interesting from climate perspective, because they were deposited during Pennsylvanian, when the atmospheric CO2 concentration were more or less similar to the present day. Although present is a bit higher, we have crossed that limit. We are at 412 ppm, but atmospheric CO2 concentrations were quite similar to the modern world where we humans existed after industrial age. So it's kind of a really nice sort of analog. You know, after Pennsylvanian, we have Permian, so which was a global hothouse, and atmospheric CO2 concentration was quite high. So these sort of, by studying such sort of formations, you can really have those sort of window into the past for current climatic transition, because we are experiencing a climate shift from ice house to a hot house or greenhouse, whichever you prefer. So the outcrops are exposed mostly on the cliffs, so you can't access all of the outcrops. So for this, we have drilled them behind the outcrop. This is a drilling sort of machine. We drilled those sort of cliffs, and we got a core. We got about more than 1.5 kilometer of cores, and a series of boreholes, almost 9 boreholes that we call O0, that we will refer to as 1 to 9. So 9 boreholes, more than 1.5 kilometer of core. And what we studied in detail this core, and so we derived a bed level classification scheme. So we have turbidites. Conventionally, previously, Ross was considered that it's only composed of turbidites, but what coring revealed is that it is kind of composed of mixed sort of flows. So you have turbidity currents, you have our favorite hybrid event beds, and you have this mass transport deposits. And there are different types of hybrid event beds that were formed by different processes. So there is quite huge process variability that we can also understand. So 9 hybrid event beds, we will call them HEB 1 to 9, 1 to 9 for simplicity. What I did is I sort of grouped them because these hybrid event beds occur in different bed associations. So certain beds occur with each other, and we have sort of divided them into those facies tracts. So basin, some hybrid beds were deposited in a basin sheets, basin floor. So there was an open basin, and those high volume turbidity currents were going into the basin and depositing a sheet system. Then we have those outer fan sort of setting, and then on top of that we have another fan system, which is kind of distributive channel lobe system. So we'll go quickly to these different facies tracts. So basin floor setting, as I mentioned, that these were they deposited the lower part, the lowermost basin part of the raw sandstone formation, and these were really high energetic turbidity currents. They traveled deeper into the basin, and these are the sheets sort of system. We encountered those sort of beds and 3 boreholes, and we just made those pretty literal sort of correlations, and you can see that these are extensive deposits. These are some cores for these type of beds, and what you can see is these are sand-rich beds with well-developed those H3 or lake-deprived emissions. We analyze them for organic carbon, for stable carbon isotopes, for rock-able pyrolysis, grain size, mud content. Long story short is that the cleaner sand part are organic poor, and the muddier sort of divisions which were deposited by those due to clay have almost 5 to 10 times more organic carbon. And the organic carbon is all terrestrial, so it was derived from land plants, all that sort of stuff. And you can also see in the thin sections the clear carbon difference, very organic poor and then very organic and mud-rich sort of deposits. We also measure their composition using ChemScan analysis. So the cleaner divisions are all quads with some purplish carbonate cementation. Muddier part mixed, so all greenish is clay, and then all yellowish is quads, and this brownish dark brown is organic matter. So really, and you can see the really chaotic sort of behavior of those thin sections. So they sort of reflect that there is no specific trend and everything was deposited suddenly. That we call en masse deposition. We got another type of beds, and we saw in this bed that within this en masse part or land-deprived divisions, you have organic carbon is preferentially fractionating towards the top. So if by weather you imagine it in a longitudinal section, its organic carbon is more fractionating towards the tail regions of the flow. So then there was a condensed section, there was a sea level rise, and then another fan system began to build up that we call outer fan sort of settings, because the beds of these deposits regard that it was deposited in some sort of outer fan, more mud-rich environment. So these are the beds, less sandy, more muddy, thick mud caps. And what you can see more or less the similar sort of trend: organic poor, sandy or turbidity current parts, and organic rich uh, muddier parts. Carbon is again all terrestrial. Then system was shut again, and there was another channel lobe system, another fan that propagated into the basin, and then we will call it a medial channel lobe system. So that system is composed of channelized sandstones with localized mass transport deposits and also hybrid event beds. Really nice photographs showing. So these core photographs just show the deposits, turbidity recurrence, and hybrid event beds in those sort of settings. Again, what we can see is the similar sort of trend: less mud in the cleaner, less organic carbon in the cleaner sand part, and quite a lot of organic carbon in the mud-rich part that was deposited en masse. And one interesting trend you can see is that organic carbon is much less in the mudstone caps, although they should have, because they have more mud, so perhaps they should have more organic matter. But why there is no more organic matter is just simply because of the difference in the depositional processes. So we just clustered all the data, and for all the beds, and what you can see that although mud caps have higher mud content, but they don't have higher organic matter content, just because they were deposited really slowly on the seafloor and the carbon was destroyed. While this mud-rich link debrides or H3 divisions were deposited by rapid flow freezing that I already talked about, and they have preserved more carbon. So there is this mechanism that really preserve organic carbon more, because clay is sort of changing the flow behavior fast and sort of burying those deposits deeper. We also observed their relationship in high resolution SEM, just to see why despite less mud these beds are these parts of the beds are storing more organic carbon. Then we realized that because mud organic particles are entrapped into this mud sort of aggregates, so mud is physically sort of protecting those organic matter particles. So it's providing kind of a post-burial preservation mechanism as well. On the basis of all those sort of observations, we came up with our model. So this is a simple cartoon that shows that from turbidity recurrence, mud and organic carbon is kind of segregated towards top or rear regions of the flow, and it's accumulated in these top fine-grained lithologies, which are prone to erosion or resuspension, and that's why they can be reoxidized or oxidized. While in the mechanism where flow dump their load, they are significantly deeply buried. So these are the H3 divisions where we have those organic carbon, which is higher in content. It's higher in its content just because there is a mud cap which is kind of protecting it. It was first rapidly buried, and then there is a mud cap above it, which is kind of providing a post-burial protection. And so from all these sort of observations, because hybrid beds and their capacity as a carbon sink has never been considered in the previous model, I think so we are the first ones who observed this phenomenon and have kind of came up with this model. And it's really important because many deep water systems, they can lack those mudstones. So there are certain cases where they are entirely dominated by those hybrid event beds. Here you can see that orange is representing hybrid beds, yellow is turbidity recurrence, and black and purplish are representing mudstones. So you can see that systems are entirely dominated by hybrid event beds. And these systems are about 100 meter thick in our case in the raw sandstone formation. So they're really sort of important to consider while estimating budgets for carbon burial in the deep sea. So just a short conclusion. Hybrid event beds are a significant component of submarine fan systems, but still a very underrepresented sink of organic carbon in the deep sea. Clay-driven sort of flow transformation provide an efficient mechanism for rapid burial of organic carbon in the deep sea environment, and clay can also encapsulate significant quantities of organic matter and provide a post-burial sort of protection. And so the main takeaway is that proportion of hybrid event beds in the deep water system should be considered while we are estimating our global carbon burial budgets and the deep sea fan systems. So with that, thank you very much. I'm open to questions. Ajay, I expect questions. That's why I went through fast.
So what I'm concerned is about, can we find any of these hybrid beds in Pakistan? Are we expecting someone, or are there any?
They are everywhere. You can find them in Hazara Formation and Lower Maqsood section, if I exactly remember it is. Yeah, you can find them in Pub. Pub is mostly channelized, but perhaps in some distant reaches you can. And definitely offshore. Yeah, offshore Indus as well, Indus fan perhaps. So yeah, there is potential. I hope Peter Clift, who is kind of an authority on Indus fan, who will talk after me, perhaps he may have idea because I haven't had the chance to look at Indus fan course. But they are because they are there in the Gulf of Mexico, they are there in offshore Morocco, they are there most of the places. So yeah. Please.
Thank you so much, sir. This is Mohammed Qasim Javed from Petroleum. Sir, I have two questions. The first question is that you showed a video in which you just showed a model. How can you compare this model from the actual one? Because if we see the turbidity flows occur when there is a subsidence and some type of there are turbidity flows and some deposition of these sediments, then how can you compare this model from the lab model as the rate of subsidence and the forces that are on the actual point? How can you establish these forces in the lab? And the second question part is that in Pakistan, where these your favorite hybrid beds are occurred, and how can you mean to say you can explain the petroleum point of view, its importance? Thank you.
Thank you for the brilliant questions. I think so. Why we do flume experiments or experimental sedimentology? Mostly because, as I mentioned, that sediment gravity flows are the largest sediment transport agents on Earth. So they are furious, really. They are really powerful, and they can really, it's really hard to monitor them directly in the natural settings. Although there are certain instances where we are trying, so we are technologically limited to monitor hybrid turbidity currents deposits and really in the natural settings. There are some instances now in the Congo fan from Pete Tolling's group, which is kind of monitoring. So then we really dig down to deposits to understand how these flow behave, and also sort of controlled lab experiments, because their monitoring in nature is difficult. Most of the universities or research institutions, they don't have money. So what they do is that they understand the deposits from the either rock record, or they sort of create those similar sort of situations in the lab just to see how these flows evolve. So definitely lab experiments have their limitations, and you're not directly monitoring and you may miss certain points, but it's really useful to really understand the overall picture, how these dynamics. Like I have shown you the impact of mud content. We can't model that in the perhaps in the natural settings, but in the lab they were convincingly demonstrated that a little variation in mud content can really change the behavior, depositional behavior of those flows. So labs are really useful. In Pakistan, as I mentioned earlier, there are certain settings. I'm not sure if pub is in the deep. If it's in the subsurface, there could be hybrid event beds. In the channelized parts, the outcrops that we have seen, I have seen one time. I haven't encountered many hybrid event beds, but I am hoping to have them somewhere in Hazara Formation on the lateral section, perhaps, or perhaps offshore enders. We can have them, yeah, but I don't have any. So I'm just saying it's a possibility. I don't have any concrete evidence for that in Pakistan.